All right, I'm going to go ahead and get started. So all right, so in this section, I want to maybe transition from what we've done before, which is that we've talked about a lot of different mathematical structures. In this section, we're going to mostly focus on the notion of counting. And the one thing about combinatorics is that even though there are some formulas and things that are and like different formulas computing m choose n, Stirling numbers, I hope that the goal of combinatorics is that, especially for working out combinatorics or problems that are on an exam or something like that,
It's not bad.
you really want to be able to gain some vision or some feeling for how these combinatorial structures work, rather than memorizing a table where you say something like, okay, distinguishable this, distinguishable this, then this, is that it's very easy in a combinatorics problem to change something around, or just to like change the wording or something, so as to confuse you as to what is distinguishable, what is indistinguishable, what are the balls, what are the bins, and it will be very easy under a memorization kind of point of view to answer these questions incorrectly. And so what I'm going to try to do here when talking about combinatorics is to help you gain some kind of intuition for how these things work. And when you're confronted with a problem, I hope the first thing that you don't think of is, you don't think of something that's like, wait, is this like a distinguishable balls, indistinguishable bins, and then like try to like come up with a formula. Instead, what you want to do between now and the exam is to develop some kind of, when you see a problem, to at least be able to feel what you're counting and then be able to reason about that and get out the right formula. And the only way to develop this is via a lot of practice. There is no perhaps short memorization way I can give you. I can give you some guidelines, but to develop that intuition a lot of times requires just working on a lot of problems. Inherently, I believe the combinatorics problems themselves are not too hard in order to grasp what you're doing, but it's hard to sometimes come up with an elegant or easy solution to count them. If we just wanted to count them, it could be easy because we could just enumerate all possible combinations. We write them all out, and then you count them 1, 2, 3, 4, 5, 6, 7. The hard part comes with trying to get that feeling, to get the right formula and allow that formula to calculate for you the number of possibilities efficiently. So here I'm going to, so in combinatorics, let's start with something that I think is an important structure in combinatorics, which is that of choosing, all right, and choose m. Now, you may be familiar with this with a formula, perhaps n factorial over m factorial, n minus m factorial. You may be familiar with this in terms of this formula, and it may be more comfortable for you maybe to think about this n choose m in terms of this formula. And that's probably because we've learned algebra for so much time and combinatorics for so little of it, that we immediately, when you are confronted with something like some symbol like this, you immediately want to convert it into a formula by which to calculate it. But one other way to think about what n choose m is imagine if you started in a combinatorics world where all you learned was combinatorics first and you had algebra come later. And in effect, if you're in that world, I want you to imagine that n choose m is effectively one symbol which represents the number of ways to select a group of m people out of a class of n. Notice I haven't quite mentioned the notions of distinguishability, but I want you to maybe try to internalize that this symbol n choose m is representing a count of the number of ways to select a committee of m people out of n candidates. And I'm using people in order to emphasize that the fact that the objects that you are selecting are distinguishable. Notice that there is no regard to the order in which they are selected, only who is in the committee and who is not. Now, to connect this with the formula here, I want to perhaps maybe give an example, that a more concrete example. Instead of using n choose m, maybe I'll say we have 10. Let's talk about 10 choose 4. And another way I can think about 10 choose 4 is committees. Well, maybe I have 10 people. I'll label 10 slots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Label these 10 slots. And I write down numbers 1 and 0. 1 being selected, you're going to select this person. 0 being that you're not going to select. And so maybe I'll do something like this. Ten choose 4, therefore, is also the number of ways to count a bit string of zeros and ones, 10 characters, 4 ones. Now, how am I going? Now, if we think about 10 choose 4 as the number of possible bit strings, 10 characters, 4 ones, how else can I think about this? Well, I can also think about this as I have 6 zeros, I have 4 ones, and I want to be able to shuffle them around. I want to count the number of orderings I'm going to be able to do this. And if I assume that these zeros and these ones all look different, then the number of orderings is 10 factorial. 10 factorial orderings, if they all look different. Let's say I label this as 0A, 0B, C, D, E, 1A, 1B, let's call this 1W, 1X, 1Y, 1Z, 1Y, 1Z. If they all look different, there are 10 factorial ways in order to order these zeros and ones. Oh, well, F here. But in fact, these zeros and ones are not distinguishable. We can't tell the difference between this 0 and this 0. In fact, if I were to swap these 2 zeros, you get the same sequence. So this 10 factorial is severely overcounting the number of possible bit strings, 10 characters, 4 ones. And how much is it overcounting by? Well, it's overcounting by the number of possible ways you could rearrange the zeros in their place and not change the bit string. So here I have 6 of these. I have 6 of these zeros, and I can rearrange those zeros however I want in these 6 spots, and nothing's gonna change about this bit string. So how much have I overcounted by? I've overcounted by the number of ways I can rearrange all these zeros. And there are 6 factorial ways to rearrange those zeros, and 4 factorial ways by a similar argument to rearrange those ones. This is in fact the same formula as here. Here we have n spaces, m of them are ones. If all the zeros and ones are different, and in fact you could tell them apart, you have n factorial ways of ordering them. But we've overcounted. We've overcounted by the number of ways to rearrange the ones. How many are those? M factorial. We've overcounted by the number of ways we can rearrange the zeros. How many of those? N minus m factorial, the remaining n minus m factorial. I want to also talk about Stirling numbers, n, m. And here we were able to have this nice little formula here. The Stirling numbers formula is definitely far more complicated. But if we think about it in that kind of combinatorics world kind of sense, what's the Stirling number of the second kind, nm? That's the number of ways to put n distinguishable balls into m indistinguishable bins, and no bin is left empty. In effect, now, when it was perhaps feasible to think of this as a formula, this we're really likely not going to want to think about this as a formula. Instead, you want to think about this as the entity describing the number of ways where you have n distinguishable balls, m indistinguishable bins, and the number of ways to sort them in so that no bin is left empty. I now want to go over that table of various types of occupancy problems, distinguishable and indistinguishable. So I'm going to this up. I'm going to draw this table maybe here. I'm going to tell you all a story. This is a story about a kindergarten teacher. This kindergarten teacher has, let's say, how many students? Let's say 15. We have 15 students. And we have let's say we have 21 candy bars. In fact, it's a very strange kindergarten because we're going to count the number of ways to give the candy bars to the students. So here, you can imagine that the students each in kindergarten, you have these cubbies, with your labeled name and something like that. So the bins are corresponding to, each student, the balls corresponding to the candy bars. So let's say we have, I'll do the balls, the bins, distinguishable, indistinguishable, distinguishable, indistinguishable. And I want to talk about arrangement, injective, surjective. So arrangements is just, how do I put them into the bins? Injective says, well, each bin can have at most one. Surjective, each bin has to have at least one. So suppose you're the kindergarten teacher, and the kindergarten teacher can tell the difference between the students, hopefully, and the 21 candy bars are like all different. So there are different kinds of candies, and we want to figure out how many ways you can put the candy bars, to give the candy bars to the students. Well, in this case, each candy bar, I take my first candy bar. And so this table is presented in the lecture notes, but I'm going to try to work through the intuition of this, which is each candy bar, I have 15 options for where I'm going to put it. I take out my first candy bar, maybe Jolly Rancher. I have 15 options for where to put it. Take a second one, maybe like a chocolate bar, Hershey's chocolate bar, 15 options for where to put it. So 15 options for the first, 15 options for the second, 15 options for the third. Therefore, total 15 to the 21 arrangements. Now, suppose we needed them to be injective. We needed a way to put the 21 candy bars into the 15 bins so that each one has at most one. Maybe this is like a health kind of thing where everyone can get at most one. But like in this case, this is probably not a great example because there are more candy bars than students, and so there's more candy bars than students. So obviously the answer is 0. But if I want to make this, I'll maybe make this a little more general. So I'll have 2 scenarios. One is this, where more candy bars than the students. Here, maybe I'll have fewer, so maybe 9 candy bars, 15 students. And instead here, I'll write down the number like 15 to the 21, but in effect, there are n balls, m bins, and I'll write a more general formula here, which is this is m to the n. For injective arrangements, I think it's more interesting to think about the second case. 9 candy bars, 15 students, everything's distinguishable or whatever. So how do we do this? Well, first we want to maybe pick which students are going to get the candy bars, right? Because they can only get one. Everyone can get at most one. So I'll first pick who's going to get the candy bars. Well, there are 15 students. I have to pick 9 of them. I have to pick a group of 9 of them. Then out of that group of 9, I need to count the number of ways to arrange those 9 candy bars. Or maybe like, candy bar 1 goes to student 1, candy bar 2 goes to student 2, but like I could rearrange who gets which candy bar. So there are 2 kind of selections here going on. One is who gets the candy bars, like who's going to get a candy bar, and then which candy bar is going to who. 15 choose 9 ways to pick the students which will get some candy bar, times 9 factorial ways to arrange the candy bars among those who will get them. I generalize this. This here is n. This fifth. So this candy bars are the balls, students are the bins. Candy bars are the balls, students are the bins. M choose n. N factorial. Now, how about these surjective arrangements? Perhaps in this case, it's better to think about scenario 1, where you have more candy bars than students. Well, first I want to distribute the candy bars into the bins. First, I maybe want to distribute the candy bars into the bins so that this is surjective, so I don't want any of them to be empty. I want to first just put them into bins. You can almost imagine this as there's like a lunch person who like gets all the bins and then like puts them all in, but like doesn't know this one's going to this one's going to this person, like doesn't know. So to the lunch person, everything's indistinguishable. To the teacher, everything's distinguishable. To the lunch person, how many ways are there to put in the 21 candy bars for the 15 students, just such that nobody gets nothing? Well, that's exactly the Stirling number NM. It's exactly 21, 15. Notice here how we didn't really think about the Stirling number in terms of any kind of formula. We thought about it as a combinatorial object, telling you the number of ways that such a lunch person can take the 21 candy bars and put them into the 15 indistinguishable bins, such that no bin is empty. Now, after that happens, it goes back to the kindergarten teacher, and whether the kindergarten teacher needs to distribute them. So now there are 15 factorial different ways for the kindergarten teacher to, maybe say this box goes to you, this box goes to you, this box goes to you. There are 15 factorial ways of arranging who gets which box. 21, so Stirling number 2115 is the number of ways that lunch person puts in the candies into the bins, that those bins go to the teacher, and there are 15 factorial ways to say like, okay, like you get this, you get this, you get this, you get this. And so if I write out the formula for this, this is n m factorial. Now let's proceed to the case of indistinguishable balls, distinguishable bins. In this case, the school decides that they don't want to buy all these kind of candy bars, and so instead they're just only going to buy one. They're just only going to buy one type of candy bar, but still we can tell the difference between which are the students. And so now how many arrangements are there? Now we have these indistinguishable candy bars, but we know which are the bins. And so here, this is in effect a balls and bins problem. This is saying, well, I've got these 21 indistinguishable balls, 15 distinguishable bins. And how am I going to put them in? This is in effect that your standard stars and bars, balls and urns, balls and bins kind of problem. I want to come back to that a little bit because I want to take care of this and this together. For at least for injective arrangements, you can imagine if you have 21 of these, or actually let's think about scenario 2. You can imagine if you have 9 of these candy bars, 9 indistinguishable candy bars, all that matters at this point is who gets the candy bars. There's no concern about like, like these 9 people get the candy bars, but then like, you get this one, you get that one. It's indistinguishable. All that matters now is who is going to get a candy bar. So how many ways are there? Well, it's just 15 students. I'm just going to have to pick who's going to get one. And so that gives you M choose N. All right, now let's talk about balls and bins. Here I'm going to use scenario 1. I have 21 candy bars and 15 students. And I'm going to do an aside here. I'm going to move this backward up. I'm going to do an aside here to talk about balls and bins, because I think it's difficult a lot of times. Perhaps some of these, I think, reasonably you could have come up with using some intuition. But I believe that balls and bins formula is something that's rather difficult to remember. It's like an n plus m minus 1, choose m minus 1, which is n, which is m, is n the balls, m the bins. And so it may be difficult to figure out exactly what is going on. And then you have to remember whether to subtract 1. If you choose m, is it m minus 1 or n minus 1? And so it's very easy for you to forget which is which. So in this case, I'm going to let's make the numbers a little bit smaller. Let's say I have 9 balls, 4 bins. And the way to think about having 9 balls and 4 bins, so remember the balls are indistinguishable. Bins are distinguishable. 9 balls and 4 bins. The way I like to think about this is if you need 4 bins, think about the boundaries in between 2 bins. How many dividers do you need to divide this board into 4 areas? Well, you need 3 dividers. I need 1 here, 1, 1. This is the first bin, this is the second bin, third bin, fourth bin. Notice that these bins are in fact distinguishable based on the relative position of these bins. So I need 3 dividers to demarcate the 4 bins. After I've demarcated the 4 bins, I can insert the balls, maybe 1, 2, 3, 4, 5, 6, 7, 8, 9. And if we're looking at this here, so we have 9 balls, 3 maybe dividers. How many ways are there to put the balls in the bins? Well, notice this arrangement here is an arrangement of putting the balls in the bins. I put 4 balls in the first bin, 2 balls in the second bin, 1 ball in the third bin, 2 in the fourth. But what is this actually? All I need to do is I need to chop these dividers shorter, and I have a bit string. This bit string has 9 zeros, 3 ones. So how many ways are there to make a bit string of 9 zeros and 3 ones? Well, that's the same thing as we have 12. We have 12 slots, and I need to pick 3 of them to have a 1. Equivalently, I can say I have 12 spots, and I pick 9 of them to be a 0. So if I have n balls and if now I have n and m, what are the total number of ways to do balls and bins? Well, I need n balls, m minus 1 dividers. Well, that's the same thing as having n zeros, m minus 1 ones. That's a total of n plus m minus 1 spaces, n plus m minus 1 spaces. And I choose out of those spaces either m minus 1 of them to put the ones, or I choose n of them to put the zeros. In the case of surjective arrangements, are we good? Thumbs up, middle, thumbs down about this? In the case of surjective arrangements, I need every bin to have at least 1 ball. So now let's talk about surjective down here. In this case, what I'm going to do, I'm going to lay out my 9 balls. And my 4 bins, I'm again going to put those 3 dividers in. Now, where are those 3 dividers going to go? They have to go in between these balls. I can't put a divider here because that means that this one's empty and everything has to be non-empty. Can't put a divider here for a similar reason. And I can't put 2 dividers in the middle because that means this one in between the 2 dividers, that bin has no balls. So if I have these 3 dividers, I need to pick out of these slots 3 slots for which to put the dividers in. How many slots are there? Well, there are n balls. So there are 9 balls here. So there are 8 slots. 8 slots that are going in between them. Notice there's 1 after each except for the last. So 8 slots. And again, I have 3 dividers. And how I need to pick how to separate this out is that I need 8 choose 3 ways, because I have 8 of these slots and I need to pick 3 of them to place the dividers. Well, how do I get this 8? Well, that's just 1 less than the number of balls that I put down. So this is n minus 1. How did I get 3? Well, 3 is the number of dividers I need to stick here. That's 1 less than the number of bins. That gives me m minus 1. Thumbs up, middle, thumbs down about this. Yeah.
It's guaranteed that no 2 dividers go into the same like.
Because I'm just selecting like 3 of these to put dividers. So if I'm selecting, so I'm saying this slot gets a divider, this slot gets a divider, this slot gets a divider. And so by that restriction, I can't put 2 dividers in the same one, because when you're doing choose, you can't choose something twice. Right, so that means I can take this and I will fill in the top. In the case of normal arrangement, that's the balls and bins, n plus m minus 1, choose m minus 1. Here in the surjective arrangements, I did n minus 1, choose m minus 1. Oh boy, I need to plug in my computer. See if this is gonna work. Wait, are you still able to hear the sound? Can somebody maybe give a thumbs up if you can hear this? All right, good. All right, so in this case of both indistinguishable. Indistinguishable balls, indistinguishable bins. Perhaps it's easiest, I'm sorry, not indistinguishable balls, distinguishable balls, indistinguishable bins. So this is the case where if we had now, instead of the kindergarten teacher giving out the candies, we have distinguishable candies. So we're back to having different types of candies, but it's the lunch person handing them out. So the lunch person doesn't know, like, like this bin is for this person, this bin. To the lunch person, all of the bins perhaps maybe indistinguishable. All this lunch distribution worker is doing is putting the candies into the bins and then like giving it to each class. So the bins in this case are now indistinguishable. I'm going to start with surjective arrangements. This is distinguishable balls going into indistinguishable bins. No bin can be empty. If you remember, that is exactly the definition of the Stirling number and m. Remember so this is directly straight from the definition of the Stirling number. How about for total arrangements? Well, for total arrangements, so the Stirling number requires that no bin be empty. But here in the arrangements, we might want to allow for our bins to be empty. And so we need to now do cases on, well, how many bins are empty? Maybe none of the maybe none of the bins are empty. In which case we would have nm. Maybe one of the bins is empty. Then that's n minus 1. maybe 2 of the bins are empty, n minus 2. And so we can make this a sum. I'm going to do this a sum of n choose k, of the Stirling number nk, where k tells you how many non-empty bins there are. Now, why is it that we don't need to multiply by k factorial? That's because the bins are indistinguishable. As long as if I have 5 bins which are filled, I can't tell the difference if these 5 bins are filled, or these 5 bins are filled, or this are filled. I can't tell the difference between any of those. All I know is that 5 bins are filled because the bins themselves are indistinguishable. There's no need to multiply by k factorial. The bins, you can't tell the difference between one bin or another. Now, where am I summing this up to? Well, how many bins can be empty? Well, maybe k equals 1. That's if 1 bin is non-empty. So everything goes in that 1 bin. Up to k equals n, all the bins are non-empty. So this is doing cases on the number of non-empty bins. In the case of injective arrangement, yeah. Huh?
Why do we go to n and not n?
Oh, you're right. Yeah, thank you.
The arrangements.
Yeah. So m bins.
He fixed it.
For injective arrangement, well, you can't tell the difference between the bins. You can tell the difference between the candies, but you can't tell the difference between the bins. So injective arrangements, if I think about the second scenario, maybe 9 candy bars, 15 students. As far as I'm concerned, I'm just going to put all the candy bars inside the bins. And there's one way to do that. I can't tell the difference between the bins. I'm just going to put 1 in each bin, and then the rest will be empty. And it's no different from if I put the 9 in some other bin, other 9 bins, because the bins are indistinguishable. If I put them in the first 9 bins, it's the same as putting them in the last 9 bins. I just put 1 in each bin and call it a day. And so here, in the number of injective arrangements, it's either 1 if you have enough bins to fit everything, if n is less than or equal to m, or it's 0, n is greater than m. What this is saying is, well, there's one way to do it if you have enough bins. You just put 1 in each bin and then leave the rest empty. Or there's no way to do it if you have too many candy bars, because there's no way to pack like an injective arrangement. If I have, let's say, 21 candy bars, 15 bins, there's no possible injective arrangement. There's no possible injective arrangement because however I put them in, some bin's just going to get more than 1. That's by the pigeonhole principle. So this effectively is a summary of all of the various occupancy problems that we've encountered this semester. I want to spend a little bit of time. I want to spend just a little bit of time talking about a combinatorial proof and also the principle of inclusion-exclusion, and then we'll go and do some probability.
So time to start.
Yeah, 34% of my favorite class 5 projects, like anything in the class.
Oh, wait, that was good.
Suppose we want to prove this in a combinatorial fashion. And I want to emphasize that in a combinatorial proof, there is effectively no algebra. There's no splitting up this stuff into like the formulas for choose. In effect, when you're dealing with a combinatorial proof, you're effectively operating in that combinatorics world where you think about these symbols representing the number of ways to choose. You don't think about these as formulas. I'm going to give a quick rundown of how the combinatorial proof works. Step one, you want to supply a counting problem. In effect, a combinatorial proof is a reverse engineering kind of technique. Normally, you're given a counting problem for which you need to find a formula. In a combinatorial proof, you're now given two formulas, and you want to find one counting problem that works, that gives you this as the answer, and also gives you this as the answer. The effect is that when you supply one counting problem and say, all right, I'm supplying this one counting problem, and I'm going to show how to solve to get left-hand side. And then show how to solve to get right-hand side. In effect, what is going on is that you've only supplied one counting problem. But by supplying that one counting problem, and you're saying, well, if I count it this way, I can get the formula on the left-hand side. If I count it this other way, I can get the formula on the right-hand side. What you're saying is that these two formulas have to be the same because they are solving the same counting problem. Your counting problem cannot have more than one answer. Therefore, if these two formulas are solving the same counting problem, they both need to be equal because they're both giving the answer to the same problem. So they both have to give the same answer. For this, I'm just going to do a quick rundown of how this would work. Part one, the way to supply counting problem, you look for the easier side. This looks complicated, but this looks easy. Look for the easier side and immediately just make a counting problem for the easier side. M plus n choose R. I'm going to do, let's say I have I need some kind of like distinguishable object. Any suggestions? Need some kind of distinguishable thing. Yeah. All right, and Jose, can you tell pigeons apart? Some other distinguishable objects. Cars. Okay. In effect here, my counting problem, I need to select, so that these are both distinguishable, right? You have to be able to tell the pigeons apart and the cars. So these are both distinguishable. And my counting problem is I want to count the number of ways to select a committee, select a group of R pigeons or cars. So you could select only cars or only pigeons, one pigeon, R minus one cars, anything in between. I'm going to do 3 first. How do I solve the right-hand side? Well, this comes directly from the counting problem. If I have m pigeons, n cars, and I have total m plus n objects, and I need to select a group of R of them that precisely is the definition of m plus n choose R. How about the left-hand side? When you see a sum, this is indicating to you probably want to do some cases. And what's the cases? Cases are on K. What does K represent here? Well, K represents this. Represents how many of the m pigeons you are picking. So for fixed K, so let's say you want fixed K pigeons. I have m choose K ways to pick those pigeons. And then out of the n cars, I need to pick R minus K of them. Well, so if I say I have to get K pigeons, well, there are m choose K ways to pick those pigeons. And well, now I need to pick R minus K remaining objects. Those R minus K remaining objects must be cars. Therefore, there are also n choose R minus K ways to pick the remaining cars. and then I sum these over all possible values of k. I could have picked anywhere from no pigeons all the way up to m pigeons. And so this gives you the total number of ways to select that group. Did I write R? Oh, right. R. Sorry, because I can select up to, I can select no pigeons, or I can select all the way up to all of them, all of the group being pigeons. So k equals 0 is I select no pigeons. K equals R is my whole group is pigeons. So sum from k equals 0 to R of this, which is the number of ways to pick that group, given that you are fixed k pigeons. Right. I'm going to skip over a bit about the principle of, I'm going to maybe just give a few minutes on inclusion exclusion, which I don't think is going to take too long, and then I'm going to proceed to probability. Yeah.
Just want to make sure, is it assuming that R is less than N or N?
I think we can make reasonable assumptions. What will end up happening is that if it doesn't really work, I think on the test, if you have time, you can check the boundary cases, but most of the time, it's most important to get the reasonable cases.
You don't see it anymore.
All right, a short aside, well, not aside, but a short thing about inclusion exclusion. The idea of inclusion exclusion is that you want to count the total number, given that you know like some individual sets, except the sets can sometimes be intersecting. So let's say that I have A is some set, you know, B is some set, C is some set, and I want to count how many things are in A union B union C. I want to count this. Now, this would be easy if A, B, and C are disjoint. I just add up the three, add up the size of A, size of B, size of C. That's fine. But it gets hard because sometimes, like, you might, what if A and B had some things in common? Then if I added up the A stuff, the B stuff, the C stuff, I would have now double counted the stuff that's in common. Even worse, what if I had like something that's in all three sets and then now I counted like those things 3 times? So the way to visualize this formula is via a Venn diagram. What is this equal to? Imagine these are my, this is my set A, this is my set B, this is my set C. What's the total number of things inside A union B union C? Well, let's first count how much is in A. That means I've counted this stuff once, this stuff once, this stuff once, this stuff once. I'm using a dot to represent how many times I've counted something in that region. Well, I'll do that for B. I'll do that for C. I'll do this here too. So now I've double counted these, triple counted this.
You can figure it out.
What do I do from here? I'm going to take away this. I'm going to take away 1 inside A intersect B. I'm going to take away 1 in here. I'm going to take away 1 inside A intersect C. I'm going to take away 1 inside B intersect C. And so now I've essentially counted everything once, except for the middle. So I add back the middle. And this gives you the way to count everything once. So in effect, when you're confused about these inclusion-exclusion problems, if you forget this formula, the way to do it is by drawing these dots on the Venn diagram and seeing how much you've counted stuff in each region and subtracting off stuff that you may have double counted adding back stuff that you need to count. I'm going to erase this, and I'm going to start with probability. Probability, we're talking about chance. We're talking about how likely something is to happen, how likely, and so we want to talk, and so in probability, we want to be able to formalize what it means for something to have some likelihood. In effect, when something has some likelihood, this is no longer a deterministic kind of process where you're certain as to what the output is going to be. In probability, we always have things that are like random experiments. Something is going to happen, and with some likelihood, and different possibilities could come up with each with different likelihoods. For example, if someone were to tell you like 48% chance it will snow tomorrow, well, you don't know what's going to happen. It might snow, that has likelihood 48%. Might not, that has likelihood 52%. And so when we talk about probability, there's always this underlying narrative where we're talking about something, a random experiment or a random thing that's happening. And so here I want to introduce the idea of an outcome. The outcome tells you what are all the possible things that could happen in this random experiment. If the random experiment is rolling a die, then the outcomes are perhaps 1, 2, 3, 4, 5, and 6. Because those are the different things that can happen. Events are and so I think one more term I should define is the sample space. That's the set of outcomes. An event is a subset of the sample space. When you think of an event, you always want to think of that event, you almost want to think of an event in some kind of Boolean kind of fashion. Either that event happens or doesn't happen. For example, if I'm rolling a die and I'm rolling 1 to 6, the sample space is 1 to 6, but the event need not be like one of them. The event is a subset of the sample space. The event could be rolling an odd number. And so the event happens if I happen to roll 1, a 3, or a 5. The event doesn't happen if I roll a 2, 4, or 6. In effect, when you think about an event, you can almost think of an event as if you think back to like automata. Automata, you have a language to tell you these are the strings that are permitted, and those strings are not. Remember, sets are modeling inclusion and exclusion. Here, when we're talking about an event happens if you when you have this random experiment. The event happens if you get an outcome which is inside that event. The event doesn't happen when you get an outcome which is outside of the event. And so, with the die rolling example is clear that we have different outcomes, 1, 2, 3, 4, 5, 6. The sample space tells you, well, what's the set of all possible outcomes, well, 1 through 6. And what's an event? Well, an event is a subset of that, maybe rolling an odd number that would correspond to the subset 1, 3, 5. If you roll a 4, that event doesn't happen. If you roll a 1, that event does happen. Are we good about this? Thumbs up. So we can write something where we can say like the probability of event A happening is some number. In the case of the dice, I'll write it out. Maybe the sample space. The sample space. That's 1, 2, 3, 4, 5, 6. An event is a subset of it. I'll make it maybe we'll do 1, 2, 3 this time. And the probability of A is telling you, well, what's the chance that this event happens? Here, I hope it's not too complicated to see probability of A is 1/2. But now let's talk about the idea of conditioning. when we talk about the idea of conditioning, I want you to kind of keep this visualization in mind. Suppose you had this box here, and this box represents the sample space, represents everything that could, all the outcomes that could possibly happen. Now you have an event A, which is a subset of the sample space. Let's say A is these outcomes. And maybe you have another event, I'll call this A. And maybe you have another event B, which are these outcomes.
And your outcome is also infinite.
Event B. Now the probability of A is simply, like how likely are these going to happen out of everything? How likely, probability of B is how likely these are going to happen out of everything. But let's say let's say we're now talking about probability of B given A. So in effect, when you're just calculating probability of A here, you're essentially like taking, how much stuff is in here, dividing by how much stuff is in total. The idea of conditioning probability B given A is that I'm now restricting my attention only to the stuff inside A. I'm certain that event A happens. So I'm only restricting myself inside this region. And out of the area of this region, how likely is it that B happens? So this is now this area divided by this area. It's possible that, let's say I had a thing C here. Maybe C is here. Probability of C is not 0. But the probability of C given A, if I only inside this A region, what's the probability that C happens? That's 0, because I'm only restricting my attention to this A section. I won't. On the topic of conditioning, I want to give an explanation of Bayes' rule. And Bayes' rule, I think, is another one of those formulas which are very, very difficult to remember, because there are lots of givens, lots of like A given B, B given A. And so I want to show you a procedure by which to do Bayes' rule so that you don't need to remember this formula.
So I think
I'm going to do a problem on the vending machine. So suppose this vending machine outputs a Coke with probability C, Sprite S, and water otherwise. And there's some conditions that, like, if Bob gets a Coke, there's some probability he either drinks it or doesn't drink it. Now, what we want to calculate is, given that Bob drinks the beverage, what's the probability he got Coke, Sprite, water? And so here I'm gonna maybe write out this problem of it. Let's say Coke, this vending machine pops out a Coke with 0.25, pops out a Sprite with 0.5. Oh, maybe I'll make it fractions. 1/4, 1/2, and water 1/4. And for each of these, there's a different probability of whether Bob is going to drink it or not. If he gets a Coke, maybe he'll more likely drink it. If he gets a Sprite, less likely. And so effectively, when you're presented with a Bayes' rule problem, the first thing you want to do is define the relevant events and write down the probabilities that you know. Here, the probability of a Coke coming out is 1/4. Here, let's say probability of Sprite is 1/2. Probability of water is 1/4. Now, Bob has different likelihoods based on what drink he gets of drinking that beverage, actually. Let's say D is drink. Let's say he drinks a given Coke. Let's say that happens with 1/3. Probability he drinks it given Sprite. Let's say that's 2/5. Probability that he drinks it given that he gets a water is 1/7 maybe. And we want to find out what's the probability. Let's say we want to find out what's the probability he gets a Coke, given that you know he drank it. How you already know this is a Bayes' rule problem is that the probabilities you know are D given the drink, D given C. But the probability you want to find is you swap them, C given D. If I wanted to find D given C, it's already provided in the problem, it's 1/3. But the hard part about this is that we now need to flip these. So when you realize that you have a probability that you know in this form, but the probability you want to find is swapped, that's how you know there's Bayes' rule. And how we're going to think about this is, imagine you're standing right here. And I'm going to draw for you, almost as if like a fork in the road, what roads he could possibly go down. What's your first fork in the road is going to be the probabilities with no givens. You're standing here, you essentially don't know anything that's happened. You want to find the one with no givens, C, S, W. I'm going to label each one, indicating the frequency or the probability I'm going to take that road. Now, let's say now you're standing at C. You either drink it or you don't drink it. What's the probability you drink it? That's 1/3. So that means the other 2/3 of the time you come down here. Similarly, I'm going to do this, 2/5, 3/5, and this D, not D, 1/7, 6/7. Effectively, what this graph is showing you is, if I am standing here, what's the probability I take this road? What's the probability I take this road? So here, what's the probability that he gets a Coke and he drinks it? Well, 1/4 of the time he comes down here. And out of that 1/4 of the time, 1/3 of the time he comes down here. So that gives you 1/4 of the time he comes down here. And out of that 1/4, 1/3 of the time he comes down here, this gives you the 1/12. I can do that similarly here. So this is 2/12, 1/2 times 2/5, which is 2/10. So now each of these probabilities are telling you, what's the probability you get a Coke and you drink it? What's the probability you get a Coke and you don't drink it? What's the probability you get Sprite and you drink it? And so on. And we want to find, out of the times when Bob is drinking, how many times does he get a Coke? So what's the total kind of outcome set that we're talking about? We're only concerned with the proportion of events where he's actually drinking the thing that he gets. So how much is that? That's 1/12 of the, so 1/12 of the total is for the Coke one, that's 2/10 plus 1/28. Out of these times when he drinks it, how many times does he get a Coke? 1/12. 3, thumbs up, middle, thumbs down. Right. Want to now talk briefly about random variables.
It's gonna work. You probably have some.
You drink.
When we were talking about random variables are, the way I want you to think about random variables are effectively like a signal. Underlying this whole discussion of probability, we've always said that there's this kind of random experiment that we're always talking about. And a random variable, in effect, is a signal for that random experiment. You almost want to think that this random experiment is being done in some way that you can't see it. And the only way you can talk about its outcome is by looking at the signals which tell you what's the like, imagine that this random experiment is being done inside like a room which you cannot see. But instead, you get the option to say, well, if you get this, flash this signal. In effect, a random variable is like a signal. And so let's say we have the underlying random experiment, which is the dice roll. we're going to roll something, and the signal tells you the number. So I roll 3, the signal comes out as 3. The random variable, rather than thinking of a random variable as like attaining a fixed value, like x equals 3 or y equals 4 or something like that, think about the random variable as representing this signal. Now I can also define the signal differently. I can also say, well, maybe the signal should output twice the number that I roll. I roll 3, comes out as 6. Maybe I want the signal to be 1, 0. So it's output a 1 if I roll an odd number, 0 even. I roll 3, it'll pop up with a 1. I want to do an example here about this would be question 20 on the review sheet. So let's say we're on a grid. So Zima is the cat of an old TA in this class, but let's say we're on this grid. And with probability P, I go 1 unit up. With probability P, I come this way. With probability 1 minus P, I come this way. Now, let's talk about maybe the expected value. The expected value is how you want to think about the expected value is that the expected value is not necessarily a value that you might attain. Maybe not even that this value, that what you expect to get. And the expected value is in essence an average. It's saying, well, we have this random experiment. If I were to repeat this random experiment many times, on average, what value is going to come out of the signal? So maybe like if I did a dice roll, 1/6 of the time is going to pop up the 1, 1/6 of the time is going to pop up the 2, 1/6 of the time is pop up the 3. But if I were to do this dice roll many times, I run this experiment many times, on average, the value that's popping up on the signal is 3.5. So here, let's define a random variable x. So let's say that x1 that's 1 if it comes this way, and 0 goes this way. In other words, x1 is representing, well, how much x increase did I get on the first move? So x1 is going to pop out with a 1 with probability 1 minus p, and pop out with a 0 with probability p. Probability p, Zima goes up, and so there's no change in the x, or it goes to the right with probability 1 minus p, it's going to pop with a 1. And so after n moves, that's just, well, how much x change did you get on the first one, plus the second one, plus the third one, and so on up to xn. Well, maybe I'll just do x. Now the expected value, the way to calculate the expected value, I'll calculate the expected value x1. The expected value x1 is just these. You're going to take each possible value and multiply it by the probability and add it all up. So 0 times p plus 1 times 1 minus p, so 1 minus p. Now, what's e of x? What's e of x here? Well, e of x here is x is just the sum of them, x1, x2, up to xn. By linearity of expectation, I can split this up, e of x1, e of x2, up to e of xn. Each of these are 1 minus p. There are n of them, so you get n 1 minus p. Now you can also think about this in terms of that like probability mass function kind of thing. Probability mass function, at least for a discrete random variable, I'm saying 0. Well, how much probability do I get a value of 0? There's p here, maybe. And how much probability do I get a value of 1? This 1 minus p. Now, in the continuous case, I'm not really going to do an example, but in the continuous case, you can also generate some probability mass function. Let's say you generate something like this. let's call this P of X. And in effect, here we're adding up 0 times this, 1 times this. In effect, here we've essentially 0 times P times plus 1 times 1 minus P. We're taking the value multiplying by the probability. Here we're again taking, we want to take maybe the value multiplied by the, I'm going to use very serious air quotes, probability. But an integral is in fact just a sum, just that those rectangles get infinitely thin. And so here the expected value, you're still summing the value times the probability. This is an infinite sum, you take the integral. Now, I want to be very, very careful about saying that this is in fact the probability of getting, like if this is like maybe like 3, that this is the probability of getting 3. In a continuous sense, this notion of a probability of getting a specific value is very, very sticky. Because if you really had an infinite like number of possible values, what's the probability that you really get precisely 3? In effect 0. And in effect, it's like, oh, well, in effect, I have 0 probability of getting this, 0 probability of getting this. So really, we shouldn't be thinking about things as saying that's the probability of getting 3. Instead, what this probability mass function does in a continuous sense is it says, well, let's say you let me be in this range. This area will give you the probability. If you want this range, this area will give you the probability. And so that's why the probability mass function, in effect, really like derives its meaning by the area underneath it. And that's why it's very important to talk about it inside an integral. Now let's talk about the variance of the x position. The variance of the x position. Let me erase this. The variance of x is equal to e of x squared minus e of x. The variance of the x position, one way is to think about it like this. But in the case of this problem, remember these random variables are independent. And intuitively, if they're independent, that means they're not really affecting each other. Yeah.
They're square on the second.
Oh, yes. Yeah, thank you. And so when these are independent, I can also say the variance of x is equal to the variance of x1 plus the variance of x2. What's important to remember is that if I had any factors here, a, in the expected value, those factors just pop out. But if I had an ax1 here, this becomes an a squared for variance. So remember, in variance, when you multiply by a constant factor, it gets multiplied by the constant factor squared. In this case, we're just going to do this. All of them are the same, so I can just calculate one of them. Variance of x1 equals to e x1 squared minus e of x1 squared. What's e of x1? We calculated that as 1 minus p. So 1 minus p squared. What's e of x1 squared? Well, x1 squared, remember, this is just a signal. So x1 squared is saying, well, tell me how much you change in x, and the signal will pop out with the square of that value. x1 squared, therefore, is equal to 1 when the signal pops out 1 with probability 1 minus p, 0 probability p. The expected value is therefore also 1 minus p. This gives me 1 minus p times 1 minus 1 minus p. There's p times 1 minus p. Adding this up, this is only for x1. So if I add it up over all n, that's equal to n times p 1 minus p. I'm gonna maybe just do one more calculation, and that would be the covariance of x and y. So if x is your x position, y is your y position. Maybe calculate the covariance for you.
That's what he does. That's what it is.
The covariance of x and y. Probably the most useful formula for this would be the expected value of xy minus the expected value of x, expected value of y. Y is just the y position. So we've calculated expected value of x. That's n times p 1 minus, no. That's n times 1 minus p. We can do a similar calculation for y. That's n times p. I'm not going to do that here yet. And then let's calculate this. What might be a little bit tricky about this is that x and y tell you like how much x change has been done, how much y change has been done. And what we could do here is we'll split this up. The sum of xi times the sum of yi. What this is saying is right here is the x1 plus x2 plus x3 plus x4. This is the y1 plus y2 plus y3 plus y4. What's the expected value of this? Well, here we have n terms which are basically like xi, yi, which are the same on the same move. Plus, well, in total, there are n squared terms. I had to subtract off the n I did here, where you have some maybe xi, yj. So I'll add expected value here. So this, in effect, is the linearity of expectation. What's the expected value of xi times yi? In the same move, if xi is 1, yi is 0. If yi is 1, xi is 0. So the expected value of this value, xi times yi, Zima can't move both up and right at the same time. It moves up, then the x is 0. Moves to the right, y is 0. So this whole thing here, 0. What's xi, yj? Well, since the moves are independent, E of xi, yj, well, this thing is just E of xi times E of yj. Since the moves are independent. E of xi, we've calculated that. And just 1 minus p, yj, p, and so this gives you n squared minus n times p times 1 minus p. I take this, and so in total, here I have my n squared minus n, p 1 minus p, and here I have minus n squared p 1 minus p. One final thing, the variance is always positive. These are always doing something squared. So the covariance can be negative. All right, so basically concludes all of basically all the key points that I wanted to make. I want you to take a step back. I want you to take a step back and appreciate what we've been able to cover. And I want you to realize that in effect, all of these things that we talked about are very simple. At the bottom of it, everything is in effect very simple because we're talking about logic, which is just truth and falsehood, sets, which are just whether things are included or not, functions, input and output, relations, formalizing the idea of less than or equal to, greater than or equal to, equals, automata, telling you what strings are valid, what strings are invalid, combinatorics, which is just counting, probability, which is just chance, in effect, all of these things, in essence, all of these things are very much simple. And so hopefully, like, even though we've done a lot of arithmetic, I hope that, like, and formalism, that you can take a step back and realize that all of these things are very much at their core very simple. But the power of this is that when you think deeply about these simple things, when you're able, when we take these simple things and build them up, you're able to form what this is, which is the foundation for all of the rest of CS. And I hope that you can take a moment to just appreciate that out of some very, very simple ideas like inclusion and exclusion, counting, chance, functions, relations, input and output, whether things are true or false, you can build up the entire field of computer science. And I hope that you'll take a step back, maybe to appreciate that out of these very simple ideas, you're able to form something that the importance of which I think needs no explanation. I just want, before you go, I just want you to know, it's been a pleasure to be your TA this semester. I'm going to miss you guys. And I really mean this. I really mean this. I'm going to miss you guys. I wish you all the best. If I can, I'll try to come to the final, but I'm not sure if I'll be able to make it. Wish you all the best. Thank you for a wonderful semester.
Ready?